Okay, let's get started. I wanted to get started right at 11 o'clock. I remember when I was in, I was in grad school, and I had this one professor who was consistently late every day. I mean, like 15 minutes late every day. And you just go, why even, come on, I don't know. All right, let's get started. Welcome to lecture 2. I hope everybody's first week is going well. A couple of housekeeping items. First off, while I'm going through this, if you haven't scanned the QR code, please do so. I mentioned this earlier, but I'll mention it to everybody here. So I teach a class in here right before this, right at the time slot, and I usually pull the QR code up at the end of class for anybody that missed it. But just make sure it says statics, because if it says structural analysis, that's the code for the last class. So just want to throw that on there. But yeah, the attendance grades are on Blackboard. I have recorded, or the first lecture recording is on the YouTube playlist. If you go to Blackboard, you'll see the link to the YouTube playlist, and all the lectures will be there. I have homework 1 assigned today. That's a typo. It's supposed to be due at 11. I'm going to fix that. It's going to be due at 11 a.m. because it's going to be due right before class. The homework is going to show up kind of like a quiz in Blackboard, because the way it's set up, it will grade the questions for you. But it is an untimed quiz, and with this quiz you can take it as many times as needed. So it's unlimited, and it'll grade the last attempt. So you'll see what I mean. But it's a pretty straightforward assignment. I made a post on Teams yesterday on how to navigate to the course notebook. I'll pull that up in class again today, or I'll pull it up today so that everybody sees that. But all of the board work and all the in-class examples are going to be on that, and it is going to get pretty loaded by the time the semester is over. I'll sort of make the point. This is a comparably sized class. This is my class notebook from another class, and it'll probably be about that long when it's all said and done. So there'll be a lot of stuff in there, and we'll use it quite a bit. But yeah, if you log into Teams, the logo you'll look for is the one that has pulleys. You'll see what I mean later when I pick that. But there'll be a link for class notebook, and you'll find it there. All right, everybody get the code? Okay. All right, so we'll do that later. Okay. All right, so we're in lecture 2 now, and what I'm going to do is a very brief review today of physics and units and dimensional analysis. I do this because, so in this course, it is nice if you have a background in physics, but it is not entirely necessary. What is more critical for your ability to negotiate class is an understanding of calculus, because we are going to use calculus somewhat later in the semester for locating centroids or centers of gravity, and so you kind of need to understand how an integral works and whatnot in order to be able to locate a centroid. Physics is nice, but it's not drastically necessary. A lot of students will take physics at the same time they're taking this class. Some of them will take it before. Either is really fine. But there is a little bit of background knowledge that you kind of need to know. If you open up a syllabus for a physics class, you will see that there is some carryover, some overlap between what they cover in their class and what we cover in here. In a Physics 211 course, these topics are reviewed sort of at a cursory level only in a week or so, and we take that one topic and spend the whole semester on it, because that's what we're doing here. So I just want to review what I think is appropriate, and then we'll get into units and things like that. Okay, so let's talk about physics. Mainly what we're going to be talking about is velocity, acceleration, what are forces. We'll talk a little bit about Newton's laws and the concept of gravity and whatnot. Okay, so we're starting basic, okay? So we're going to start with the concept of classical motion, how stuff moves, okay? I told you in the last lecture that we are going to be exploring a specific subset of physics, which is called mechanics. I mean, the title of the book is Vector Mechanics for Engineers, okay? So mechanics is usually started or initiated by a discussion, bless you, by a discussion of classical motion. So the way that we start out a discussion in physics about motion is we say, all right, let's just take a basic object. Like here's an object and it is moving, okay? And we will define its motion at any point in time, or its position at any point in time by some function. We'll call that x. So it's x as a function of time. So at some time, here's where it is. And at some other period in time, it's now here. So we would graph that essentially. As time changes, what is its position, okay? Now, this is where the calculus comes in. What we can do is differentiate that function, and we could say, all right, let's take the derivative of position with respect to time. And if you remember from calculus, the derivative is another way of describing a rate of change, okay? In other words, the rate of change in this case with respect to time. So how fast position is changing, okay? We have a name for that in physics. We call it velocity, okay? Velocity is the rate of change of position, okay? If you haven't had a background in physics, it is common to use the term velocity and speed interchangeably, okay? But velocity and speed have very different, well, not very different meanings, but they have different meanings, okay? And basically, can anybody tell me what the difference is? What is the difference between speed and velocity?
Velocity indicates direction, so it can be negative.
Exactly right, okay? Velocity contains direction, okay? So, if we want to maybe speak more broadly, speed is a quantity that contains only a magnitude, whereas velocity contains both a magnitude and a direction, okay? And it is what is the difference between speed and velocity. Everybody with me so far? Okay, we can also further differentiate velocity. We can say, now let's figure out how much velocity changes, okay? And if we figure out how much velocity changes, we say, what is the rate of change of velocity? We have a name for that. We call it acceleration, okay? Acceleration is the rate of change of velocity. Or if it's the first derivative of velocity, it's the second derivative of position, okay? So that's where that term comes from. And honestly, you can actually go further. I mean, there's terms like for jerk, which is the third derivative. If you actually look it up, there's actually like a snap, crackle, and pop. I'm not making that up. The first two derivatives are really what we find to be the most inherently useful in classical mechanics, okay? Now, something here that I haven't really talked about on the slide is the fact that there are some letters in these equations that are bold, okay? Some of you may have some experience with vector math before, some of you may not, okay? But any time in this course, or really in math and physics in general, you have a formula where certain terms are bolded. Like for example, if we look at this acceleration formula, the letter A is bold, the letter V is bold, the letter X is bold, everything isn't. Bold terms refer to vectors, okay? Anything that's bolded is in reference to a vector. Now, what I will probably do if I was writing this by hand is I would say, oh goodness, is I would say, hold on, there we go, is I would say A like with an arrow over it, dv over dt with an arrow over it, something like that, because I can't really write. I could say, A, but it'd be kind of hard to differentiate. The arrow over the A and the arrow over the V helps me differentiate that is in fact a vector, okay? So we're going to be very cognizant of what's a vector and what is a scalar throughout the course. So, and what is the difference between a vector and a scalar? Vectors contain magnitude and direction. Scalars contain only magnitude, so it's like speed and velocity. So just throwing that out there. Okay. Everybody with me so far? All right. So this is just basic, fundamental, classical motion, okay? Let's talk about Newton's laws. And I imagine that even if you've never had a university physics course, you've at least kind of heard these, okay? So the first law says that an object is at rest or in motion, and if it is at rest or in motion, it will stay that way until it's acted upon by an outside force, okay? And we will actually have different ways of describing what is a force. How would we define it? But for now, what we will say is that a force is an action on a system that will increase its tendency to translate. Yeah, so we'll get to that. Okay, so that's the first law. Object at rest or in motion will stay that way until acted upon by an outside force. The second law says that an object's rate of change of momentum is proportional to how much force you're putting on it. Now, if we were to write that as a formula, we would say that an object's rate of change is directly proportional to applied force. If we're talking about rate of change, we're saying that the force equals the derivative of the momentum. And momentum is defined as mass times velocity. But mass is a constant, we can factor that out, and the derivative of velocity is acceleration. So F equals ma, right? I'm sure you all probably heard that before, right? F equals ma. The third law says that all forces between two objects exist in equal magnitude and opposite direction. Okay, we will use these throughout the semester in different ways, and these three laws are integrated into our principle of static equilibrium, which we will be using throughout the entirety of the semester. Okay, everybody okay on that? Okay. Now, there's sort of a fourth law. It doesn't really get lumped into these three, but it is just as critical. It is the law of universal gravitation. So what the law of universal gravitation states is that there are two objects out in the universe, out in space. Okay? Those two objects each have an independent mass. So we'll call them big M and little m. Okay? What Newton's law states is that two objects out in space have an attractive force between them, okay? And that attractive force is proportional to the product of those masses divided by the distance squared, okay? So what we say is that attractive force equals big M times little m over r squared times this term g. And this term g is that constant of proportionality in our known universe. We call it the universal gravitational constant. This is the number for the gravitational constant. Just to level with you, we're not going to use this in this class, so you don't have to worry about, oh, is it a 0.43 or 0.42? We're not going to use it in here. In Physics 211, that might be another story, but in here, we're just not going to worry about it. I'm just putting this out there to say that we will not use this term, but this law is important to what we do in this class. Why is it important to what we do in this class? We do not use this general form of the law, but we use a very specific form of the law, and that specific form is related to right here on planet Earth. Because if two objects have an attractive force between them, and I say, okay, let's take the universal gravitational constant, and for the numbers that I plug in, let's take the gravitational constant, and let's take the mass of the Earth and the radius of the Earth, and I take big G times big M over r squared. What that term is the acceleration due to gravity, okay? So, I mean, is there an attractive force between the Earth and objects here near us? Yes. Here's an eraser. Here's a big old Earth under. Boom, it's attracted, right? How is it attracted? By the acceleration due to gravity. In fact, if you open a physics textbook and you plug in the universal gravitational constant and look up the mass of the Earth and the average radius of the Earth and plug it in, you will get pretty darn close to 9.81 meters per second squared. It's not exactly 9.81 meters per second squared for a couple of reasons. The Earth is not uniformly dense, it's not a perfect sphere, but you're pretty close. You know, it's pretty darn close, okay? This formula we will use a lot, that the weight of an object equals its mass times the acceleration due to gravity. That we will use a lot, okay? Now, Acceleration due to gravity. I imagine most of you probably knew about 9.81 meters per second squared. I imagine did everybody know about the US version, 32.2? I'll write those down. So we are going to interchange both of them. And I will go ahead and tell you just right off the bat, bless you. This class is not a very demanding class or punishing class in terms of unit conversions. It's not going to be that challenging, okay? I will go ahead and tell you that a class like Engineering 216 or your Mechanics and Materials class in Biomedical, I think it's 302, that one might be because there are a lot of unit conversions to get from stresses and strains to deformations. There's a lot of that going in there. We're not really going to be dealing with that. To put it in perspective, a lot of what we're going to be doing in here is dealing with summing up forces. Well, if all the forces are all in the same unit, the units don't really become a problem no matter what they are, whether it's pounds or kilonewtons, it doesn't really matter. So as long as everything's consistent, which for most of our problems they are, it's pretty, the units issues are pretty chill in here. Okay. But you do need to know both the acceleration due to gravity in both SI units and US units. So for SI, we're going to use 9.81 meters per second squared, or we're going to use 32.2 feet per second squared, dependent upon which system that you use. Okay, so those are going to be our values. So far, so good? All right. Okay, let's talk about the unit systems. And yes, we are going to be using both. I'll go ahead and get on my soapbox a little bit about this. I don't think that there is an engineer worth their salt that would try and honestly claim that the US unit system makes more computational sense than the SI system. It's harder, 12 inches in a feet, 5,280 feet in a mile. Like, I get it, but until Lowe's start stacking lumber in SI units and not US units, like that's what we have. It's kind of hard to, like, I'm operating in the world as it is, not as, as I would want it to be. And we buy yards of concrete, we drive miles, so in my opinion, we do kind of need to understand how to use both, because while we have US unit systems being used in the real world, we also have metric systems being used in the real world. But I also think it makes you a stronger engineer to be able to navigate both. So we are going to use both, but again, not going to be that demanding in here. Okay, so our standard units for mechanics are as follows. So if we're talking about the international system or SI, things like the meter, the second, the kilogram, those are going to be our standard unit systems. So velocity, its standard unit is meters per second. Acceleration, its unit in meter per second squared, very common. The most commonly what I'll call derived unit in SI is a Newton. So a Newton would be 1 kilogram times 1 meter per second squared. I imagine most of you've probably heard of that at some, by now. That's going to be a very common unit that we use in here. In US units, the feet, the second, the pound. So one difference between US units and SI units is that the standard unit is the kilogram, and then we derive the force unit based off that, whereas in US units it's sort of inverted. The pound is the standard unit for force, and then we back calculate our mass unit, which is the slug. We don't really use that all that much, but I just want to throw that out there for completion's sake. So the Newton is the mass times the acceleration. The slug is the weight divided by the acceleration. So just wanted to throw that out there. Okay. SI unit prefixes, I imagine we've all seen this. We're not going to be doing any 10 to the 24th prefixes or anything like that in here. So this is what you would find in any science textbook, and what I did is highlighted the rows that I have been an engineer for 10, 15 years. This is what I've used. I don't really see me using anymore. The only time I ever use things like this is when I'm buying hard drives. I mean, just the truth. Beyond that, when it comes to actually performing computations, I've never really gotten out of these unit systems all that much. Maybe if you're looking at material science, you're getting into nanoscale, but that's about it. We're not going to be doing anything outside of these highlighted ones, I think, in this class. So just want to throw that out there. Okay. Some additional notes on units. Most unit conversions in SI are on factors of 10, so there's not really a whole lot that's probably noteworthy. But in US units, a couple things that I did want to mention. First off, the inch. We are going to be seeing things in inches, and I'm hoping we all know that there's 12 inches in a foot. One unit that you probably have not heard of is a kip. Okay, a kip is a very widely used unit in civil engineering applications, and a kip is just shorthand for a kilopound. So 1 kip is 1,000 pounds. Okay, so you'll probably see me use kips quite a bit in here, and so if you're wondering what a kip is, that's what a kip is. It's just 1,000 pounds. So I wanted to just get that out of the way now, so that you'll know what I'm talking about. A lot of the problems that we're going to do in here are going to be dealing with forces that are of significant magnitude. I mean, just think about how heavy this building is, and think about trying to express that in pounds. It would just, the numbers would get silly, So we use kips as a way of, managing them a little bit. So, like, I teach a course in, a senior level course in steel design, and it's not that uncommon that we'll be designing columns for 500, 600 kips. That's pretty common. So, all right. Any questions? Everybody good? Okay. So, one of the things that you need to be able to do in scientific computations is unit conversion. And for a lot of my sort of first 2-year classes, you've probably done this in other classes before, but I still think it's a healthy exercise to just make sure that we're all comfortable with it again. I have taught courses from the freshman level to the graduate level and everything in between, and I have had students at every level that have still struggled with unit conversions. It is a fundamental skill to be able to do as an engineer, and it's easy to miss. I mean, there's been a lot of engineering failures as a result of over the years because of this. Hold on, let me go back. I've had a number of situations where this is an issue. So we're going to go through the process of doing some very basic unit conversions. Now, what we're going to do is we're going to convert these terms, like 73 miles per hour to meters per second, and this term, which is a little bit more complicated here. Now, what I want to do is I want to use these facts up here. These are going to be my accepted unit conversions for the purposes of the example. Those are going to be the values that I use. If you've never had to do this before, basically what we're going to do is we're going to figure out how to get this term into meters per second. And what we're going to do is we're going to multiply it by successive definitions of the number 1. Okay? If I take a number and I multiply it by 1, what do I get? I get the same number I started out with, right? So, for example, I propose that 1 does not equal 0.3048. Nobody would agree that 1 equals 0.3048. But 1 foot does equal 0.3048 meters. Okay? So if I write this as a fraction, like 1 foot divided by this, or this divided by 1 foot, that fraction would equal 1. Okay? So all I'm going to do is keep multiplying it by these successive fractions and start canceling out units until I get the answer that I want. That's basically a unit conversion in a nutshell. Okay? Now, let's just make sure. So here I am in the statics channel for the class. In order to access the notebook, the calculations that I do, you click this class notebook button up here. Okay? So when you click that, it will take you to a Teams interface right here. And when this loads, you can click this book right here. I have this opened up in a separate OneNote browser. But you click this little book right here, and you navigate to Content Library and click this little folder right here, and you will see the calculations I'm about to do. So the cool thing is when this is done, or if there's anything that you missed on the board, it's all right here. So it's kind of nifty. I'm going to take this and make it a little smaller. Okay, that way we can see everything. Okay, so I'm going to convert the following. I'm going to walk you through the first one, and then I'm going to have you give me a little bit more help on the second one. Okay, so 73 miles per hour. If you've never done this in chemistry, a lot of times you'll see that they'll draw a big old table and do it like that. Have you all done that in chemistry? You've probably seen it like that. You know, there's no real wrong way of doing it, but I'll show you what I do. Okay, so we have 73 miles per hour. Okay, actually, let me move this down here a little bit so that I got a little bit more room. Okay, what I'm going to do is I'm going to successively multiply this by fractions to get it into meters per second. Let's start off with the time first. Okay, so I'm dealing with hours. Okay, I want to get hours into seconds. Okay, so let's start off with something simple. I know a simple unit conversion for hours to minutes. What is that? 60 minutes in an hour. So if I write a fraction that says 60 minutes in 1 hour, that fraction is equal to 1, right? So if I were to multiply that fraction by this, I would get a term that is representative from units. Now, is this the right way to write that fraction? No, okay? In fact, what I want to do is I want to write 1 hour over 60 minutes. And why do I want to do that? Because the hours will cancel. It's sort of like if you have 2x equals 3y and you divide both sides by 2, the 2's cancel, right? It's kind of the idea. So what I'm doing is because the hours was on the bottom here and I'm trying to get rid of hours, I put the hours on top over here, okay? So if I wanted to get this into seconds, now what do I do?
60 seconds.
There we go. So I would say, so do I do,
Do 1 minute on top.
there we go. There we go. So far, so good? So now, if I were to just carry this through, I would take 73 times this, and I would be left with miles per second, right? But that's not what I want. I want meters per second, okay? Well, I know how many meters are in a foot. Maybe if I can get miles to feet, I can get that working. How many feet are in a mile? 5280. So what I'm going to do is I'm going to say 1 mile is 5,280 feet. So I'll use a different color. That's going to cancel that and that, right? And then now what I can do is I can say 1 foot is 0.3048 meters. So that I can cancel that and that. So what I'm left with is seconds and meters, which is exactly what I was after. That's what I was after, is meters per second. And then in terms of what I plug into my handy-dandy calculator, what I'm going to plug into my handy-dandy calculator is 73 times 1, so you can ignore the ones, times 5280 times 0.3048 all over 60 times 60 times 1 times 1. So all I'm doing is I'm just taking all the numbers up top, all the numbers on the bottom, a big old fraction. That's all I'm doing. So if you wanted, you could, obviously you could ignore the ones. You don't have to worry about them. Anything times 1 is itself. And I'm going to get a number. And for the purposes of our calculation, we'll say 2 decimal places. And I'll say a word about significant figures here in a bit, because I'm sure some of you are thinking about that. So does anybody have a value for me? We'll say 2 decimal places. 32.63. Do I have a second on that? In other words, did somebody else get that? Okay. I often do that. If somebody will give me an answer, then I'll ask for a second, like I'm asking for a second on a motion. Just make sure everybody's awake. All right, meters per second. And there we go. And what I'm doing here is I'm writing ANS above this, shorthand for answer. So I'll usually circle that at the end of a problem. So, sound good. Make sense? Can everybody read my handwriting? Is that big enough? If you can't read it, let me know. My feelings will get hurt because you made fun of my handwriting, but then I will make it clear. That was a joke, not a very funny one. All right. Okay. With me so far? Okay. All right. So now we're going to do this next one. Okay. This next one here is 63.9. Okay. Now I wrote it in a specific way. I would probably never do this, moving forward, but I'm writing it this way. This is pounds per square inch, or PSI, right? Most engineers will write it as PSI and they'll just move on. But I'm writing it this way because I want you to get into the context of that this is a force per length squared and this is a force per length squared. Because that's going to get into a further topic of dimensional analysis, which we'll talk about here in a bit. So what I'm going to write is I'm going to write 63.9 pounds per inches squared. Now, you'll notice that the pounds has a little subscript. It's LB sub F. When you get into fluid mechanics, you'll notice that there's, just between pounds force and pounds mass. There are nuances in how you would handle that, so I'm just sort of getting used to that notation. In here, if you were to write pounds versus pounds sub F, I'm not going to care. It's not going to really matter in here, but I'm just throwing that terminology at you so that you see it later. Okay. All right. Let's deal with the force first. So the pounds. So we need to get pounds to kilonewtons. Okay. So let's do that. Okay. So how do we want to do this? We'll say okay. What do I put in here? What goes in this fraction? We'll start off by using this. So what goes in here? The newtons on top. Bless you. So 4.44822 newtons, then 1 pound force. So I need to make that a subscript. Okay. So that'll get rid of that. Okay. So now we're in newtons, but I need to get newtons to kilonewtons. Okay. So what is going to be my fact? Like, how do I relate kilonewtons to newtons?
Would it be like grams to kilograms, where
There we go.
1,000 grams is 1 kilogram?
There we go. So our fact in this case, if we want to write it up here, 1 kilonewton is 1,000 newtons, right? So if I'm writing this out, tell me what I write. Like, tell me what goes here. What goes here and here? Does the newtons go on top or on the...
1 kilonewton.
There we go, yeah. Yeah, so the 1 kilonewton goes here. 1,000 newtons goes here. Okay. So we've got to where we wanted to get on the pounds because we're now at kilonewtons, right? We're done with the forces. Now we need to deal with the length units, okay? So we have inches squared, okay? So here's our conversion factor. We know that 1 foot is this. So let's get the inches into feet. So let's just ask a simple question. How many inches are in a foot? 12, right? So that means that I can say 12 inches in a foot, right? Am I missing something?
Square.
It's squared. Now there's a couple ways you can handle that. You could square the whole thing or do it again. Why am I doing it again? Because this is inches times inches, right? This is inches times inches. There are 12 inches in a foot, but there are 144 square inches in a square foot. You see what I mean? So you got to do both. Okay? So I want to make sure that that's clear, that we need to do this twice. Okay? All right. So the same thing with the meters. Okay? So now what I've done is I've canceled the inches, but I've got 2 feet on the top. So if I were to carry this out, I'd get kilonewton per feet squared. I need kilonewton per meter squared. Okay? So what I'm going to do is I'm going to say, okay, 1 foot, put the foot up top, 0.3048 meters. But again, I need to do this one twice. Okay? That. Getting ahead of myself. So that now I can cancel a foot, cancel a foot, cancel a foot, cancel a foot. And I'm going to do that equals down here because I'm running out of space. So what I would put in my calculator, I'm going to skip the ones, but I would say 63.9 times 4.44822, 12. Here, let me, there we go. And then 1,000 times 0.3048, 0.3048. So in other words, I'm just, here in blue, this is just what I would plug and chug in my handy dandy calculator. And we'll just say let's say 2 decimal places again. This is good enough. So if we do 2 decimal places here, what will we get? 440.57. Do I have a second on that? Awesome. Okay. And then my units are what I wanted them to be, kilonewtons per meter squared. Or 440.57. Does anybody know what a newton per meter squared is? Anybody remember that? A newton per meter squared is what's called a pascal. So you could also say kilopascals. If you haven't seen that unit before, you will see that in engineering. Pascals you're going to see that in reference to both stresses in like beams and columns and things like that, or shafts or what have you, or in fluids, because that's how we would express pressure in SI units. So you're going to see pascals again, trust me. All right. Any questions? I will make a remark. I'm going to make a remark which might surprise you a little bit. I tend to not really get all that worked up about significant digits. I'm sure some of you are thinking about that. Like, is that the proper number of significant digits? I'm really not worried about it. A lot of the calculations that we do in here, significant digits really don't affect the be-all, end-all method or final result. I mean, to give you a sort of humorous example, we're not really changing the number of bolts in a spliced connection in a bridge based on significant digits. Like, we're just not doing it. So I'm not saying it's not important. There are situations where it very much is important, laboratory settings and so on and so forth. It's just a lot of what we're doing here is large-scale force vector analysis, and it doesn't really affect the methods. I honestly tend to not get all that worked up over it. So the homework assignment that you're going to do in here, the way it's going to work is you do the problems and input the values in Blackboard, and then Blackboard will automatically grade the answer, but it has a range. So if you round it a little bit differently than your friend, shouldn't affect the answer. The answer should be the same. So, sound good? All right. Does anybody have any questions about this? Everybody good? Okay. So just to show you what your homework assignment actually is, I'm just actually going to show you. So for those of you that were worried that the homework assignments in here were going to be disastrously difficult, That's your homework. Let me move this over. That's it. So I'm giving you 3 problems, and I want you to convert these values from this unit system to that unit system. That's it. See what I mean? That's due Friday, but that's it. So now I got a couple more things I want to talk about today, but in terms of what you need to do for your homework, that's it. Not too bad, right? Okay. All right. Any questions about the idea? Okay. All right. I want to spend the last little bit of class, and we may not get to finish this topic, but I want to talk about the idea of dimensional analysis. Okay? Dimensional analysis is sort of akin to being able to convert units, but it's a little bit more higher level. So let me give you an example that's near and dear to my heart. Okay? So this is a very fundamental problem in classical mechanics. This is a beam. We say that this beam is simply supported. You'll know what that means later on this semester. But suffice it to say that these 2 supports at the end of the beam are classified as simple supports. And they're classified that way because they don't resist what are called end moments. We'll get to that later. Okay? Whenever we place a load on a structure like this, the structure responds by deforming. You can see that the beam is flexing. It's kind of smiling at us a little bit. A very common question in mechanics, both in civil engineering, mechanical engineering applications, you name it, is how much is it deforming? In other words, the beam started out flat, now it's bent. How much is it bent? Okay, that distance. Okay, that is a very common question in engineering mechanics. Okay, now the formula to compute that for this very specific problem is right here. In other words, that deflection is calculated as PL cubed over 40 ADI. Okay, and those terms have a very specific meaning. So P in this case is however much load you're putting on it. Okay, that's whatever this force is. L is the length of the beam. Okay, all right. E is what's called an elastic modulus. So E is it is a material property. So there's a different elastic modulus. Sometimes it's called Young's modulus. There's a different Young's modulus for copper than there is for aluminum, than there is for steel, what have you. Different materials have different E values. And then finally, a moment of inertia. The moment of inertia is a property of like what the beam looks like. It's what's called a section property. It's like the section property would be something like the area, or where how big around it is, or what's the center of gravity, what have you. Now notice that I have given you US units for what these terms should be. In other words, if you plug and chug into this formula, you must use a consistent unit system, otherwise your answer isn't really going to make any sense. Your load has to be, if your load is in pounds, then the E value has to be in PSI. The beam length has to be in inches, and this moment of inertia, I know this is a weird term, we'll talk about this more later this semester, how the moment of inertia is inches to the 4th. I know that's kind of weird, but trust me, that's right. And the reason why is if you actually plug and chug and carry those units out, so like on the top, if I took pounds times length cubed, pounds times length cubed, I get this. On the bottom, if I take PSI times inches to the 4th, I carry it out and I get inches, okay? Which, first off, the question is, does the answer make sense? Well, what am I calculating? I'm calculating a deflection. The goal was to figure out how far that was, and the answer is in inches. Does that make sense? Yeah, that makes sense, okay? Couple other things. Notice how I went from here to here. Is there anything that I forgot when I went from here to here? What don't I have? I have the P here, the L here, the I here, the E here. What do I not have here?
Constant.
The 48, right? Why did I not include the 48? I didn't include the 48 because I'm performing a dimensional analysis. If I take 2 inches and I multiply it by 48, I get 96 what? Inches, right? The unit isn't going to be affected by that number, right? So if I'm trying to perform a dimensional analysis, the number really doesn't matter. Does that make sense? Okay, don't worry, we'll talk about this a little bit more on Friday. But here's where like the real value comes in. Okay, here's where, like, if you're wondering why would I do this, here's where the value comes in. Okay, so we're trying to figure out the deflection in a beam. Okay, now let's ignore all this math. Okay, okay, so we're in a classroom right now. Right there behind you, that's a column. Okay, in that little, so the little jutted out in the wall right there, there's a column keeping the building upright. There's another one right there behind you. Okay, between that column are beams, right? Somebody tell me how long you think that beam is. Yes. From here to here.
20 foot.
What was that?
20 foot.
Hold on. I think you're right, but what did you say?
Feet.
You said 20 feet, right? He said 20 feet. That's a natural definition for how long a beam is. What would happen if you put a beam length of 20 foot in this formula? It wouldn't make sense, right? You see my point? Okay? The purpose of this exercise is to ensure both that your formulas make sense, that they're yielding answers that comport with reality for what you want, but if you start plugging and chugging and your answers don't make sense, why? Well, a good answer might be you plugged in feet, but the units don't work that way. You need to convert that beam length to inches in order for everything to be consistent. And I don't care if we're talking about US units or SI units. This is consistent across the board. If we were talking in the land of SI, it would be very, convenient to express a beam length in meters. But we're talking about a deflection in millimeters. Those aren't the same thing, right? So what I'm talking about is that exercise of ensuring that what you're plugging in makes sense. Okay? Everybody with me so far? All right. We're probably not going to have time to explore this, but I want to illustrate the problem that we're going to look at. We're going to come right in on Friday and start this problem, but I want to show you the context of what we're looking at. I'll talk about the context today, and then we'll do the dimensional exercise on Friday. What I have here, this is a very famous equation in engineering mechanics, and everybody in this room will be exposed to this at some point in your engineering education. This is an equation from fluid mechanics, okay? What this equation does is it characterizes the amount of energy in a conduit that's carrying a fluid. Now, we define that energy with three terms, okay? So the energy equals this plus this plus this. So if we're adding terms, what must be true about the units?
They're the same.
They have to be the same. You can't add 7 feet to 12 seconds. That doesn't make sense, right? They all have to be consistent units, okay? Now, in fluid mechanics, the total amount of energy in a pipe is a function of the pressure term, how much pressure is the fluid under, the velocity term, how fast the fluid is moving, and the fluid's elevation. We have a specific name for those in fluid mechanics. We call that pressure head, velocity head, elevation head, okay? So a good example is, so if you're ever let's say you're in a town that is very, very flat, like you're in the Midwest, right? And you want to have water pressure in people's houses. How do you get water pressure when there's no changes in elevation? You take that water and you raise it with a water tower. That's what water towers are for, right? To supply the energy necessary in the water system so that when people turn on their water faucets, the water doesn't drip. It actually has some energy to it. Now, how do you do it? You take the water and you stick it up, right? So that's what this is. This is what's called Bernoulli's equation, okay? So just keep this factoid in the back of your head. Probably like next year when you take a fluid mechanics course and somebody mentions Bernoulli's equation, you go, oh, okay. So what we're going to do, and we'll do this on Friday, is we're going to plug and chug into these terms, and we're going to see if the values that we plugged in are dimensionally consistent, okay? We'll do that on Friday. I'm going to pull up the QR code one more time for anybody that missed it, but that's all I have, everybody, and I will see you all on Friday.